Welcome back to the Deep Dive. Today we're getting into something you hear about constantly in climate talks. Carbon capture and storage, CCS.
And CCUS, the utilization part, too.
Right, CCUS. So if you've ever wondered if these technologies can really do the heavy lifting assigned to them in those big climate targets, well, this deep dive is definitely for you.
Yeah, climate change, it demands huge cuts in CO2, especially from those tricky sectors, heavy industry, fossil fuel power.
Cement, steel.
Exactly.
Yeah.
Chemicals, gas processing, and CCUS, CCUAS are often pitched as, well, essential tools for decarbonizing those.
Absolutely. And you see big players like the IPCC, the IEA, they really lean on these technologies in their pathways, suggesting they can handle maybe 15, even 17% of the needed cuts by 2050.
That's the vision, yeah. But hitting that kind of scale, that speed,
Yeah.
it faces some pretty serious real-world hurdles.
Which brings us to the core question we're digging into. Just how feasible are these really ambitious targets for CCUS and CCS, especially when you look at, say, history and the practical side?
Precisely. And we've got two really good sources to help us unpack that. First, there's a research article from Nature Climate Change.
Okay.
It looks at feasibility by comparing CCS growth to how other big technologies actually rolled out historically.
Interesting. And the second one?
That's a review paper from Geoenergy Science and Engineering. It dives more into the nuts and bolts of the technology itself.
Regulation economics, too.
Exactly. It gives us a sense of why scaling up might be so tough from a practical angle.
Okay, great. So let's start by getting a handle on the scale. What the climate pathways want versus, well, where we actually are.
Right. So the IPCC's 1.5-degree goal, it often relies on negative emission technologies.
Things like BCCS and DACCS. Bioenergy capture, direct air capture.
Yeah, those are included. And they need to remove a truly staggering amount, 10 gigatons of CO2.
Annually.
Annually, yeah, by mid-century.
10 gigatons. And what about the IEA's goal just for CCS itself?
Their 2050 goal is specifically for capturing and storing 5.6 gigatons of CO2 each year, mostly from industry and power.
Okay, 5.6 gigatons. What does that translate to in terms of, building stuff?
It means needing to bring online something like 75 to 150 large new capture facilities.
Every single year.
Every single year, globally, between now and 2050.
That pace just sounds incredible. So how does that ambition stack up against today's reality?
Well, one of our sources really lays out the gap. Based on current deployment rates, the plans we see now,
Yeah.
we're maybe looking at achieving only about 10% of the CO2 storage needed by 2050 in many scenarios.
10%?
10%. It's a pretty stark gap between the model projections and, actual projects getting built.
It really is. And that leads right into the core question from that Nature Climate Change paper you mentioned.
Exactly. Can the current push for CCS actually get it on track for the Paris climate targets? Is it realistic?
So how do they tackle that?
They didn't just accept the targets. They compared the planned and required CCS growth to how other big policy-driven technologies actually grew historically.
Like what? Nuclear?
Yes.
Solar?
Yeah, nuclear power, wind power, solar power. They looked at it across 3 typical phases of how a technology deploys.
Okay, what are those phases?
First, the formative years, then an acceleration period, and finally, more stable growth.
Let's start with phase 1 then, the formative years.
Yeah.
The study puts this roughly before 2030.
Right. Usually the first 5-10 years, this is where the tech gets proven at scale, tested, adapted, initial projects hopefully get going.
And what's the story for CCS here, historically?
Well, the challenge is we've sort of been here before with CCS. About a decade ago, there were quite ambitious plans.
Especially for power plants.
Yeah, particularly in the power sector. And frankly, most of them just didn't materialize.
How bad was the failure rate for those past plans?
The study looked at plans between 1972 and 2018 and found a really striking number. 88% of the planned capacity was never actually built.
88% of what was planned.
That's right. And in the electricity sector, it was even higher, over 90% failure rate.
Wow, over 90%. That's sobering. It really shows planning isn't building. So the study uses that history to estimate what's feasible by 2030.
Yes, if you take the capacity that was planned as of 2022 and you apply that historical 88% failure rate,
You get
an estimate for operational CCS capacity in 2030 of only around 0.07 gigatons per year.
0.07. That number is just tiny compared to those multi-gigaton goals for 2050 we talked about.
It is, and even compared to the 2030 targets in many pathways.
So did they try to figure out a sort of best-case scenario for 2030, an upper limit?
They did. They calculated what they call an upper feasible bound. That reaches 0.37 gigatons per year.
Okay, 0.37. Still way below the big goals, but better than 0.07. What does it take to get there?
Well, even that is pretty optimistic. It assumes planned capacity doubles again by 2025.
Which is a big assumption.
A very big assumption. And it assumes the failure rate for all those plans drops dramatically, down to the level seen in the early U.S. nuclear power build-out.
And even that failure rate was?
Still around 45%, so not zero.
Okay. So 0.37 GTIR is the optimistic ceiling for 2030, based on history. How does that number compare to the actual climate targets for 2030?
Well, the IPCC's 1.5-degree pathways, they have a median target of 0.9 GTIR by 2030.
0.9. And the IEA?
Their latest net zero pathway targets 1 GTIR for 2030.
Okay, so even the most optimistic feasible number, 0.37, is less than half of what the IPCC median or the IEA needs for 2030. That's a huge mismatch right at the start.
It is. The study's conclusion here is pretty blunt, really. Hitting those ambitious 2030 targets, it looks almost definitely out of reach.
Based on current pipelines' likely failure rates?
Yeah.
Drawing from history?
Exactly.
What about the slightly less ambitious 2-degree pathways? Are their 2030 goals more achievable?
Their median is 0.3 GTIR by 2030.
Ah, okay. So that is within that feasible range, 0.07 to 0.37.
It is potentially achievable, yes. But it still requires boosting those plans by 2025 and getting that failure rate down significantly, somewhere between 45 and 60%.
So possible, but not a slam dunk. Still needs big improvements.
Definitely requires improvement over past performance, yeah.
And didn't the study also find that a lot of the climate models just assume growth by 2030 that looks unrealistically fast anyway?
Yes, that was a key finding. They found 76%, 3/4, of the 1.5-degree pathways and 42% of the 2-degree pathways.
Assume growth by 2030 that's faster than this historical analysis suggests is feasible.
Precisely. It really kind of highlights how some modeling assumptions might be a bit detached from the on-the-ground reality of getting these complex projects built.
That 88% historical failure rate for plans just really sticks with me. Does the other source, the Geoenergy paper, give us clues about why it's so hard? Why did those plans struggle?
It really does help connect the dots. The Geoenergy paper looks at the practical side of CCUS, and it sheds light on why that failure rate might be so high, why scaling is hard.
Like what? Cost.
Cost is a huge one, yes.
Yeah.
The paper points out the capture technology itself is usually the biggest chunk of the expense, often 70–80% of the total project cost. 70 to 80% just for capture. So high upfront costs are a major barrier.
A major barrier to getting projects financed and approved, absolutely.
Okay, high costs. What else makes it tough in those early stages?
Well, the Geoenergy paper also talks about just the technical complexity. Trying to bolt on capture tech to an existing factory or power plant?
Not always simple.
Not simple at all. You
No.
can hit the plant's efficiency. It might need big modifications. That adds engineering challenges, risk, more cost.
And finding the storage site.
That's another huge piece discussed in the second paper. Finding suitable geology, doing the assessments, the whole permitting process. That all takes time, adds uncertainty, especially early on.
Right. All these practical things feed back into why it's hard to turn plans into reality.
Exactly. The theoretical potential is one thing. Deploying it widely is another.
Okay. So that's the challenging formative phase. Let's move to phase 2 in the study, the acceleration period. This is roughly 2030 to 2040. That's right. This is where if the technology takes off, you could see, maybe 10, 20 years of really rapid, almost exponential growth.
And what did this study estimate as a feasible range for CCS capacity by 2040, based on those historical comparisons?
They came up with a range between 0.95 and 4.3 gigatons per year by 2040.
It's quite a wide range. It depends on how well things went in phase 1 and how fast it accelerated.
Exactly. It depends on that 2030 starting point and the rate of acceleration, benchmarked against things like wind or nuclear.
So what does it take to hit, say, the middle ground, the median 2-degree pathway goal for 2040?
The 2-degree median is about 2.4 gigatar by 2040. To get there,
You need
to start from that more optimistic end of the 2030 range, 0.26 to 0.37 GTIR. Remember, that already requires big improvements.
Right.
And then you need to accelerate as fast as wind power did globally back in the 2000s.
Wind grew really fast then, didn't it? Driven by policies, costs coming down.
Very rapid growth, yeah. So that's the benchmark for the 2-degree goal.
Okay. What about the even tougher 1.5-degree goal? The median there is 3.8 GTIR by 2040.
Yeah, To hit that level, you need the absolute most optimistic start in 2030, that 0.37 G-Terrier number.
Which was already a stretch.
Right. And you need to accelerate even faster at a pace like nuclear power in the 1970s.
Boy.
Or like FGD flue gas desulfurization technology in the 1980s. That was put on coal plants really quickly to deal with acid rain regulations.
So really intense periods of build-out, often driven by specific mandates or crises.
Exactly. Very rapid deployment phases for those specific technologies.
And were most climate pathways realistic about needing that kind of extreme acceleration?
The study found that even setting aside the slow start, another 14% of both 1.5 and 2-degree pathways still assume acceleration between 2030 and 2040. That's just unrealistically fast compared to those historical examples.
Okay, so if you combine the problems, the slow start in phase 1 and the need for potentially unrealistic acceleration in phase 2, how many climate pathways actually pass both feasibility checks?
When you put both constraints together, only about 10% of the 1.5-degree pathways in the IPCC dataset make the cut.
Only 10%. And for 2 degrees?
It's better, but still only 44% meet the feasibility constraints for both the formative and the acceleration phases.
That really filters down the number of scenarios that look historically plausible.
It does significantly narrow the field, yes.
All right, let's quickly touch on phase 3, stable growth after 2040. Growth usually slows down then.
Yeah, typically growth rates level off as markets saturate or other limits appear. The challenge here is just sustaining that large-scale growth over decades.
And how did the pathways look there compared to history?
The study normalized growth rates to market size for a fair comparison, and they found that even in this later phase, most pathways show CCS capacity growing faster than global nuclear ever did.
Faster even than recent wind and solar growth relative to market size.
Yes, faster than even recent wind and solar deployment rates, relatively speaking.
And didn't the study add a sort of caution about using nuclear or renewables as perfect analogies?
Yes, that's an important nuance. They pointed out that nuclear and renewables often got their big boosts from energy crises.
Right, the 70s oil crisis for nuclear.
Exactly. And recent energy security worries have pushed renewables. CCS doesn't really have that same kind of acute crisis driving it right now. Climate change is urgent, absolutely, but it's maybe not the same immediate driver as an oil shock.
So using those crisis-driven growth rates as a benchmark for CCS might be overly optimistic.
It might be, yes. That's the suggestion.
Okay, so if only a small fraction of these climate pathways meet all these feasibility checks, slow start, acceleration, stable growth, what does that mean for the total amount of CO2 captured over the century, say by 2100?
It means the total cumulative capture in these pathways that look historically feasible is significantly less than what many IPCC scenarios envision.
How much less?
The study found that pathways meeting all three constraints capture less than 600 gigatons of CO2 by 2100, even at the 95th percentile, so towards the high end of feasible.
Less than 600. Hence the original scenarios we're aiming for.
Up to 1,400 gigatons.
Wow. So potentially less than half the total CO2 capture assumed in the really ambitious scenarios.
A really substantial difference, yeah.
And didn't they run a sort of hyper-optimistic, unrealistic scenario just to test the limits?
They did. Even if you assume planned capacity doubles by 2025, and there are 0 project failures after that, which is completely unrealistic.
Right.
And growth matches the absolute fastest historical rate ever seen, like that FGD tech.
Even then,
the total cumulative capture by 2100 is still considerably lower than what's in the full range of IPCC pathways.
so very few pathways survive all these checks.
Tiny percentages, really, depending on the exact assumptions. Maybe 1 to 4% for 1.5 degrees, 3 to 14% for 2 degrees.
It really feels like this historical lens suggests models relying on super fast, super scaled CCS might be bumping up against real-world limits on deployment speed.
That's the core argument, yes. The theoretical need might be high, but the feasible rate of actually building this stuff, based on past experience, looks much slower than many pathways assume.
Did the study mention alternatives?
It did note that some alternative pathways, like ones focusing heavily on reducing energy demand, can meet climate goals without needing such historically unprecedented CCS growth. And those pathways do tend to meet these feasibility constraints.
That's a really valuable perspective, grounding these huge targets in reality. Okay, let's switch back to the geoenergy paper now, getting into the practicalities, which helps explain why scaling is so hard.
Absolutely. It gives a good overview of the tech. We mentioned capture costs being huge.
70–80%.
Yeah. And there are different ways to capture the CO2 depending on the source. Pre-combustion, post-combustion, oxy-combustion.
Can you give a quick example of each again, just briefly?
Sure. Pre-combustion, like at a hydrogen plant, grabbing CO2 before burning the fuel, the Port Arthur example. Post-combustion is common for power plants, taking CO2 from flue gas after burning like SAS Power or Petronova.
Okay.
Oxy-combustion burns fuel in pure oxygen, makes CO2 easier to grab. And then there's direct air capture, DACCS, pulling CO2 straight from the air, like that planned oxylocarbon project.
Right. Each with its own complexities and energy costs.
Definitely.
Okay, so you capture it. Expensive, complex, then you have to move it.
Transport, yeah. For big volumes, pipelines are usually the way to go.
And the CO2 is often moved in a special state.
Supercritical state, usually. It's like a dense fluid under high pressure and temperature.
Yeah.
More efficient for moving large amounts.
Got it. And then the final step, the crucial part, storing it safely underground, permanently. What are the challenges there?
Storage is absolutely key for CCS to work for the climate. You need the right geology, deep underground formations.
Like saline aquifers or old oil fields.
Yeah, deep saline aquifers, porous rock full of salty water or depleted oil and gas reservoirs are common targets. The paper notes the theoretical storage capacity globally is enormous.
Like 17,000 gigatons or something. Way more than needed.
Exactly. Huge theoretical potential. But turning that potential into actual, usable, permitted storage sites, that's where the practical hurdles come in.
It's not enough just to know a spot might work.
Right. You have to prove it's safe, get approvals, build the injection wells and infrastructure. That's a big process.
And how does the CO2 actually stay down there? What keeps it trapped?
Several mechanisms, the paper explains. First, maybe an impermeable cap rock holds it like a lid structural trapping.
Okay.
Then, as it moves through the rock, tiny amounts get stuck in pore spaces, residual trapping. Over time, it dissolves into the existing fluid's solubility trapping.
And a really long-term one.
Mineral trapping. Over potentially hundreds or thousands of years, the dissolved CO2 reacts with rock minerals to form solid carbonates, basically turns back into rock.
Permanently locked away. But how important each of those is depends on the site.
Very much depends on the specific geology, yeah.
The paper looked closely at using old oil and gas fields. What's the good and bad there?
The good is you often know the geology pretty well from drilling for oil or gas. Maybe you can reuse some wells or infrastructure, potentially cutting costs.
Makes sense. The downsides.
Well, managing pressure changes is critical. If the pressure drops too much after injection stops, the CO2 could potentially turn back into a gas.
Which is more mobile, harder to contain?
Exactly. And there can be problems right near the injection well. Things like cooling effects, ice-like hydrates forming, or salt dropping out of the water.
All potentially blocking the flow.
Yeah.
Reducing injectivity.
Right, making it harder to push the CO2 in.
What about enhanced oil recovery, EOR? Using CO2 to get more oil out. That's related, right?
Very related. It's been done for decades, especially in the US and Canada since the 60s or 70s. A lot of the CO2 used historically was from natural sources, but now human-made CO2 is used too.
And does it actually store the CO2?
It definitely shows you can inject and store millions of tons underground. That part is proven. The paper suggests EOR could store a fair bit globally, maybe 30 gigatons.
If the CO2 stays there after the oil is out.
That's the key condition, yes. The long-term containment after EOR operations finish.
And making sure it does stay there needs good monitoring.
Absolutely critical. The paper mentions things like monitoring wells, seismic surveys, especially repeating them over time, 4D seismic to track the CO2 plume.
Gravity measurements, tracers too.
Yes, all tools to ensure it's secure and detect any movement. Though figuring out exactly where the CO2 has spread can still be challenging.
And quickly, in CCUS utilization, how does using the CO2 stack up against just storing it environmentally?
The paper looks at global warming potential, GWP. Generally, just storing it geologically has a lower GWP, a better climate outcome, than using it to make certain things.
Like chemicals or fuels.
Yeah, things like dimethyl carbonate or biodiesel mentioned in the source, their life cycle emissions can be higher. EOR's GWP is also noted as higher than just pure storage.
So not all utilization is equal from a climate perspective.
Definitely not. It depends heavily on the process and the product's fate.
Okay, so let's pull this all together again. We have the historical patterns showing slower than hoped for deployment from the Nature paper, and we have all these practical technical hurdles from the Geoenergy paper. It paints a pretty clear picture of why scaling up is tough.
It really does. We can kind of list the core challenges now, drawing from both. First, those high project costs, both upfront and running costs, especially for capture.
Big economic barrier.
Huge.
Yeah.
Then, the technical side. Improving capture efficiency, minimizing that energy penalty.
Finding and proving up suitable storage sites, that whole process.
A massive undertaking, yeah. Then ensuring that storage is secure for the very long term. Preventing leaks. That's vital for climate and public trust.
Navigating the regulations, which are still developing.
Needs a supportive framework. Building the transport infrastructure pipelines, mainly.
And public perception, social acceptance, local community concerns about safety, impact.
Very important. Opposition can stop projects. Plus, even technical details like impurities in the CO2 affecting transport or injection.
That's a comprehensive list. It really shows the complexity. So for you listening to this, someone trying to stay informed on climate solutions, what's the main takeaway?
I think the key thing is when you hear about climate targets and strategies, it's really crucial to understand the feasible speed of deployment for technologies like CCUS, not just the desired speed or the theoretical potential.
Right. It's easy to see a graph showing massive CCS growth by 2040 and just assume it'll happen.
But this deep dive, looking at these sources, it suggests that while CCUS is probably a necessary tool, its track record.
Those high failure rates, the slow start.
Exactly. And all those practical challenges we just listed, they suggest that the really rapid, huge scale up in the most ambitious scenarios, it might just be unrealistic compared to how we've actually built complex infrastructure before.
It helps you grasp the nuance, doesn't it? It's not just, does it work? Because, yes, projects show it can work.
The real question is how fast and how widely can it realistically scale? Acknowledging those real-world obstacles, cost, complexity, sites, pipelines, public acceptance, that's vital for judging if a climate pathway is truly feasible.
Adds that critical thinking layer.
For sure.
So the big picture takeaway seems to be CCUS and CCS are seen as vital, the storage potential is theoretically vast, but the speed and scale needed in ambitious climate plans might be historically unprecedented and face serious ongoing hurdles, technical, economic, social.
Which leads us to a final thought, something for you to consider. Given these potential limits on how fast we can realistically deploy CCS at massive scale based on history and practical challenges, does this mean we need to put even more focus, maybe even greater urgency on other strategies?
Like what? Energy efficiency, changing how we consume energy.
Exactly. Do those other mitigation levers need to be pulled even harder and faster to make sure we meet our climate goals?